20,000 lives vanished in a matter of minutes as a wall of black water obliterated entire cities. 2011 remains the year Japan received the most brutal warning from nature, proving the ocean recognizes no mercy. Why did the nation respond by constructing the most expansive defensive shield in the history of humanity? It would seem an impossible task to fortify an entire coastline against the Pacific, but without this $12 billion investment, the next seismic event would find the population utterly defenseless against the absolute fury of the sea. One can notice how a concrete scar now stretches across 400 kilometers of the coast. This is not merely a wall, but a monumental engineering feat designed to prevent a repeat of past tragedies. It gets more complex further on. The country does not simply float on the water, but sits directly atop a geological time bomb. To understand the scale of this struggle against the ocean, one must look down into the dark depths where sunlight never penetrates. Japan is positioned exactly at the convergence point where four gigantic tectonic plates collide. Imagine four stone continents continuously pushing, scraping, and fighting for space with relentless pressure. This is the Ring of Fire, a zone that produces more than 500 earthquakes every single year. The Earth there never sleeps. When the accumulated subterranean tension finally ruptures, the seafloor is thrust upward with unimaginable physical violence. This displacement does not create a standard wave, but a moving mountain of water with immense kinetic energy. During the events of 2011, the old defenses of Japan, consisting of walls 7 or 8 meters high, were treated like children's toys by the surge. The water transitioned over them as if they did not exist, exerting pressure that crushed old concrete and twisted structural steel. It is visible how the sheer force of the tide rendered previous engineering philosophies obsolete. At first glance, the destruction was absolute, but in reality, it forced a fundamental shift in defensive strategy. Engineers realized a terrifying truth. It was not enough to simply build higher. They needed to reinvent the physical structure of the coastline itself. The primary mission evolved from merely stopping the water to a strategy of buying time. This precious window of minutes provides the opportunity for people to reach higher ground and survive the initial impact. Consequently, the construction of this 21st century Great Wall began under a new set of parameters. The process is only gaining momentum. One can notice the precision with which the new barriers are integrated into the topography. The camera glides along the massive embankments where reinforced materials are layered to withstand seismic vibrations. Everything only gets more complicated as the design must account for the specific fluid dynamics of a tsunami. The engineering focus shifted toward structural resilience and the dissipation of energy. Every meter of the 400-kilometer barrier represents a calculated defense against the movement of the tectonic plates. This massive shield stands as the current culmination of Japan's efforts to stabilize its future against the unpredictable shifts of the Earth's crust. Thus, the transformation of the coastline reaches a state of readiness for the challenges that lie ahead. One laboratory. This is where the survival of an entire coastline begins before a single grain of sand is even moved on the beach. Why must scientists recreate the apocalypse in giant water tanks before pouring the first drop of cement? It would seem that simple observation of historical events would suffice for design. However, by repeatedly hurling tons of water against scaled wall models, researchers discovered that sheer height was not the ultimate defense. At first glance, a tall barrier appears impenetrable, but in reality, the immense force of a tsunami would snap a purely vertical structure at its base like a dry branch. One can notice how the water pressure concentrates at the foundation, seeking the weakest point of resistance. The solution lay in the geometric shape of the structure and, more importantly, in what remained hidden beneath the surface of the Earth. The regional coastline of Tohoku in Japan presents a geological nightmare consisting primarily of soft, unstable, and treacherous sand. Building a concrete rampart 15 meters high on top of such a substrate is equivalent to balancing a heavy truck on a wet sponge. The process is only gaining momentum as engineers address this fundamental instability. If a tsunami were to strike a wall built on untreated sand, the ground would liquefy and the entire structure would collapse forward. The engineering response was both brutal and invisible to the naked eye. The true strength of this defensive line is not found in the visible concrete, but in the massive reinforcements buried deep within the coastal shelf. Drilling machines resembling equipment from a science fiction narrative began the transformation of the landscape. They did not merely excavate soil, they fundamentally altered its physical properties through mechanical and chemical intervention. Steel and concrete piles were driven 25 meters into the earth, a distance equal to the height of an 8-story building. Everything only gets more complicated as the stabilization continues. One can notice how the equipment injects liquid cement directly into the sand layers, fusing the loose particles into a solid mass of artificial rock. This creates an unbreakable root system designed to anchor the barrier against the most violent hydraulic forces. It gets more complex further on. The objective was to ensure that even if a wave overtopped the crest, the foundation would not tilt or give way. The wall would remain standing like a stone sentinel, refusing to cede ground to the ocean. With the foundation finally prepared for this industrial war, the construction army arrived on the scene. 30,000 people, including engineers, laborers, and crane operators, formed a massive workforce dedicated to the project. It only looks obvious to call this a team, but in reality, it was a specialized military-scale operation. A fleet of heavy machinery consumed diesel and operated 24 hours a day for 7 consecutive years. The logistical challenge was nearly impossible to comprehend. It involved the construction of a continuous, flawless barrier spanning 400 kilometers. This distance is equal to the journey between London and Paris, but realized entirely in military-grade reinforced concrete. Transition to the next level. One can notice the hypnotic and terrifying scale of the work as the metal skeleton takes shape. First, thousands of tons of steel rebar with metal bars as thick as a human arm were woven into complex industrial cages. This serves as the internal skeleton of the structure, providing the necessary tensile strength. Without this dense webbing, the rigid concrete would shatter instantly under the tension of a massive wave. Then came the liquid heart of the rampart, the industrial concrete. High-pressure pumps operated with a steady rhythm, pushing a gray avalanche of material into the waiting molds. Section by section, the massive blocks began to rise from the reinforced ground. The material leaves the molds, transitioning into a calm stage as the concrete cures into its final form. Thousands of tons of reinforced concrete and high-grade steel form the primary line of defense, rising block by block against the horizon. Why is a vertical wall insufficient to stop the ocean? A flat surface would eventually fail because water strikes it with the kinetic energy of a high-speed bullet train. To dissipate this immense impact, engineers deploy a geometric secret weapon known as tetrapods. One can notice these 4-legged structures resembling giant concrete toys scattered along the shoreline. But in reality, each individual unit weighs several tons, and they are stacked by the thousands directly in front of the seawall. Their primary function is the creation of controlled chaos. When a massive wave makes contact, the water does not strike the solid wall like a single crushing hammer. Instead, the liquid is forced to break apart, swirling and foaming as it loses momentum between the thick concrete legs of the tetrapods. They successfully transform a lethal strike into a manageable push through pure physical resistance. The process is only gaining momentum. It is the application of physics to tame the raw force of nature, yet a significant logistical challenge remained for the designers. Japan depends entirely on the sea for its survival. Fishing vessels, massive cargo ships, and tourism boats require constant passage into and out of the harbors. If the entire coastline were sealed behind a continuous wall, the national economy would effectively vanish. In such a scenario, coastal cities would suffer from economic starvation. How do you allow ships to pass while simultaneously stopping a tsunami? The Japanese engineering solution was the development of massive steel guillotines. In high-traffic ports, they installed gates that look like something from a cyberpunk future. One can observe how the equipment gradually integrates into the landscape. Yet these structures are terrifying in their efficiency. There are 2 primary categories of these gates. The first is the vertical drop gate. A massive steel plate weighing several hundred tons remains suspended between 2 towering concrete supports. It stays in its elevated position as ships navigate safely beneath it every day. But this is not the limit of the system. The moment seismic sensors detect an earthquake on the ocean floor, the mechanism changes. Hydraulic motors release the heavy locks, and the massive plate descends rapidly. The port is sealed within seconds as a wall of steel blocks the entrance. The second type of barrier is even more technically impressive, consisting of gates that rise directly from the seabed. These structures lay flat on the ocean floor, remaining invisible and allowing ships to navigate over them without obstruction. When the alarm sounds, air pressure or hydraulic systems force the gates upward. An instant barrier emerges from the depths. A significant challenge here is the constant threat of corrosion. Salt water destroys metal surfaces rapidly through oxidation. These gates must be capable of functioning perfectly even after sitting idle in salt water and abrasive sand for 30 years. A single failure or a rusted hinge could lead to the flooding of an entire city. Therefore, the maintenance of these mechanical beasts is treated as a matter of absolute national security. Japan did not stop its engineering efforts at the surface level. At first glance, blocking the water seems like the only solution, but in reality, sometimes the best strategy is to move beneath it. The construction of underwater tunnels represents perhaps the most audacious feat of all. The camera glides along the blueprints for these deep bay crossings. Forget traditional drilling machines that simply cut through rock. This process transitions to the next level of complexity as the narrative moves toward the subterranean structures. The material is ready to move to the next processing phase without haste. 200 meters is the length of each individual concrete segment used by Japanese engineers to construct underwater passages through a method that initially seems to defy physical logic. Why would a construction team build a massive tunnel on dry land only to intentionally sink it into the depths of the ocean? It only looks obvious to build directly on the seabed, but in reality, constructing these elements in controlled dry docks ensures the structural integrity required to withstand immense hydrostatic pressure. This specific technique is known as the immersed tube method, and it relies on the fabrication of monolithic components before they ever touch the water. The scale of these structures is immense. 730,000 tons is the weight of a single segment, a figure that surpasses the mass of a fully loaded aircraft carrier. Engineers must oversee the casting of dozens of these concrete giants within the confines of specialized dry docks. But this is just the beginning. One can notice the slow movement of valves as the docks are eventually flooded, allowing the displacement of water to lift the structures. Powerful tugboats strain against the tide as they drag the floating concrete monsters into the open sea. It is visible how the vessels fight against unpredictable currents and wind shifts to maintain a precise trajectory. The equipment gradually maneuvers these segments toward their final coordinates in what functions as a slow and high-stakes industrial ballet. The process is only gaining momentum. Precision becomes the absolute priority once the sinking operation commences. At first glance, submerging a 73,000-ton block seems like a matter of brute force. But in reality, the segment must be guided into the total darkness of the seabed to align with the previous section. A deviation of only a few millimeters would compromise the entire structure. Everything only gets more complicated as the segment nears the ocean floor. If the connection is not perfectly flush, the seals will fail under the weight of the water, leading to a catastrophic breach. The pressure at these depths would easily crush the concrete blocks if the alignment were even slightly off. Thus, the massive segment eventually settles into its designated cradle, completing its transition from a dry dock to a functional underwater artery. Ballast tanks are gradually flooded with water to force the massive tunnel sections to descend slowly toward the seabed. Why is the immersion speed controlled with such agonizing precision? At first glance, the sinking looks like a simple mechanical drop. But without a gradual increase in weight through water intake, the buoyancy of the hollow concrete structure would cause it to tilt or fracture during the transition through the currents. Sonars and high-frequency lasers guide the descent through the murky depths. One can notice how the equipment gradually adjusts the orientation of the segment as it nears the foundation. The process is only gaining momentum. A giant rubber gasket seals the interface at the exact moment the two massive pieces make physical contact on the floor of the ocean. It is visible how the immense pressure of the surrounding water pushes the segments against one another with a force of thousands of tons. This physical phenomenon makes the seal increasingly tighter as the depth increases. The force of the sea itself is utilized to ensure the interior remains perfectly dry. It gets more complex further on. Engineers cover the entire structure with layers of heavy stone and protective sand to bury the tunnel permanently beneath the seabed. This armor shields the concrete from anchors and shifting currents. Motorists will eventually travel through this corridor at speeds of 100 kilometers per hour. They will move forward without knowing that millions of tons of ocean water are pressing down just a few meters above their heads. The structure literally gains life after the concrete dries and the heavy machinery departs from the site. These walls and submerged tunnels are far from being dead stone. They possess a complex nervous system. One can notice how hundreds of electronic sensors are embedded deep within the concrete layers during the initial casting. Everything only gets more complicated. Sensors monitor the external water pressure, the vibrations generated by heavy trucks, the air temperature, and even the smallest displacement of the surrounding soil. This data flows in real time toward control rooms that resemble command centers used by space agencies. The equipment ceaselessly records every fluctuation in the environment. If a microscopic crack appears in the reinforcement, the engineers receive an immediate notification. If the seabed shifts by as little as 1 millimeter, the alarm sounds throughout the monitoring station. High stakes demand this level of constant vigilance. The molten stream of data ensures the safety of the entire underwater passage. This ensures the integrity of the work as the construction phase reaches its conclusion. $12 billion is the staggering financial weight invested in a project where the margin for error is non-existent. Why invest such a colossal sum into a barrier that cannot fully halt a massive tsunami? It seems counterintuitive to build a wall that the ocean might still crest over. But the strategic objective lies not in total dryness, but in the physics of energy dissipation, as the structure is engineered to fracture the lethal momentum of an incoming surge. The process of maintaining this defense is a continuous confrontation with the natural elements. Automated underwater robots equipped with high-resolution sensors glide along the submerged foundations to detect structural fatigue. Maintenance teams work systematically to clear drainage channels, ensuring the hydraulic integrity of the system remains absolute for the moment of impact. One can notice how the metallic arms of the ROVs maneuver through the dark currents to inspect every inch of the base. But this is just the beginning. Simulations conducted by engineers reveal a critical technical reality regarding the wall's performance. The barrier reduces the physical impact of a wave by 30 to 50%. Instead of a supersonic wall of water obliterating everything in its path instantly, the resulting flood becomes a slower, more predictable inundation. This serves a singular, vital purpose: the acquisition of time. 5 minutes or 10 minutes represent the narrow window required for a successful evacuation. It is the duration needed for the elderly to reach higher ground or for school staff to move children to safety zones. This concrete scar, stretching across 400 kilometers of the Pacific coastline, does not represent human arrogance against the sea. The movement of tectonic plates and the inevitable rise of the ocean are recognized as unstoppable physical constants. At first glance, it is merely a gray line of stone, but in reality, it is a technical shield designed for human persistence. It functions as a testament in steel and stone, stating that while the coast may be struck, it will not be defenseless. The wall is not a promise of immortality, but a calculated bet on the survival of the population. Everything only gets more complicated when the sirens eventually sound. This cold mass of reinforced concrete will stand as the solitary physical buffer between the kinetic energy of the ocean and the inhabitants of the shore. This is the point where complex civil engineering intersects with the primal instinct of survival. 19,000 tons of earth and rock must be processed to extract a mere 260 grams of gold. This is roughly equivalent to the weight of a single standard smartphone. How is such a minute quantity of precious metal separated from an almost incomprehensible volume of ore? The process is only gaining momentum. It is a technical narrative of a luster that originates in the subterranean dark, marking a journey from ancient geological formations to the finality of a gold bar. Thousands of tons of rock split apart under the force of industrial crushers to reveal the microscopic particles within. One can notice the dust settling in heavy clouds as the primary grinding stations begin their work. The story of this metal is one of extreme ratios and mechanical precision. From here, the transformation moves to the next phase of processing. 4,000 tons of gold are extracted annually across the entire globe, marking the sheer scale of the industry behind this precious metal. Why is this specific element pursued with such intensity compared to other materials found in the crust? One might assume its value is merely a social construct, but the answer lies in its physical invulnerability, as gold does not rust, fade, or corrode under any natural conditions. It remains one of the few substances on Earth that never requires a secondary proof of its worth, standing as a permanent anchor of confidence. 184 years ago, specifically in 1848, a single discovery in a California stream redirected the entire course of North American history. A handful of glittering flakes triggered the most prominent gold rush of the 19th century, causing tens of thousands of individuals to abandon established farms and cities. At first glance, the migration was a chaotic scramble, but in reality, it was a massive shift in the global labor force, driven by the hope of rapid enrichment. The process is only gaining momentum as modern exploration techniques replace the primitive pans of the past. Dozens of thousands of seekers pushed westward, driven by the prospect of power they could physically hold in their hands. The metal manifests throughout the modern luxury sector, appearing on high-performance supercars and even as edible flakes atop steaks that cost several $1,000s per serving. One can notice how the material transitions from a raw geological find into a manufactured marker of status. It seems simple to categorize gold as mere jewelry, but in reality, it has served as sacred objects and elite household utensils since the Neolithic era, dating back more than 6,000 years. Rumors once circulated regarding a brilliant gold card associated with the name of Donald Trump, with some claims suggesting a value of $5 million. It was even whispered that possession of such an object could influence the granting of American citizenship. Whether these items are functional tools or purely symbolic, they represent ambition that a person can wear. It does not end at this stage, as the gold must first be liberated from impenetrable subterranean vaults. Equipment gradually penetrates the deeper layers of the earth, where the metal remains hidden from the surface. It is visible how the search for deposits requires extreme patience, as the ore does not reveal itself without significant mechanical effort. The camera glides along the transition from historical surface mining to the complex industrial operations of the present day. Everything only gets more complicated as the hunt for the metal leads into two entirely different environmental worlds. Boulders split with a crack during the extraction phase, moving the material from the darkness of the depths toward the processing facilities. Before the gold can be locked away in high-security vaults or displayed in high-end showrooms, it must be isolated from the surrounding rock. Transition to the next level involves shifting the focus to the specific geographical zones where mining reaches its peak. From here, the journey moves toward the technical challenges of the terrain. $1 a day is the entire budget for survival in a region frequently described as living atop vast gold reserves. Why do families choose a life of such extreme hardship under a scorching sun? The answer lies in the red dust that coats everything, where gold does not glitter in shop windows, but remains hidden beneath a landscape of interrupted childhoods. Families, including children far too young to spell their own names, grasp rusted shovels and follow their parents into dry, relentless soil with the singular hope of unearthing a few precious flakes. This gold mining is not a profession, but a desperate lifeline. It gets more complex further on. One can notice how the health of these children is the true currency spent as they grow up inhaling mineral dust instead of pursuing dreams. Their classrooms are the muddy banks of rivers, and their toys are industrial tools. For them, the metal is never a symbol of status or wealth. It is the only physical chance to survive for another 24 hours. One portable metal detector and a pair of trained ears are the only tools used to begin a standard day of hunting. It seems simple at first glance, but in reality, the process relies on acute sensory focus and geological knowledge. Miners walk with slow, deliberate steps, their eyes fixed on the parched earth while listening for the faint electronic pulses of the device. Every beep provides a brief window of hope, but the labor is never left to chance. Experienced miners identify specific geological indicators, searching for gold deposits around quartz, slate, or ancient alluvial paths where the metal once traveled. The process is only gaining momentum, Once a signal is confirmed, the team initiates the excavation and the physical toll begins. Tens of meters are excavated into the earth using nothing more than shovels, pickaxes, and raw human strength. The camera glides along the vertical drops where shafts grow deeper without the assistance of any modern machinery. In certain sectors, miners utilize rough tree trunks to provide structural support for the tunnels. Yet the mechanical risk of a total collapse remains a constant physical reality. As the depth increases, the workers must crawl through narrow horizontal passages that are barely wide enough to accommodate a person lying on their side. Every hole serves as a high-stakes gamble. A tunnel might result in an empty vein, or it may reveal ore bearing enough value to equal a full month of wages. Everything only gets more complicated as the raw material reaches the surface. Heavy sacks filled with earth are secured with manual ropes and hoisted upward by basic pulley systems. These bags are piled in staging areas to await mechanical crushing. Once the rock is pulverized, the material is moved to a separate zone for a delicate and hazardous chemical intervention. Transition to the next level. This stage involves the introduction of mercury into the sediment. Although mercury is a documented neurotoxin, it remains the only accessible chemical in this environment, capable of dissolving gold to separate it from surrounding impurities. The equipment gradually processes the mixture, allowing the mercury to bind with the microscopic gold particles. The heavy metal mixture sits in shallow pans as the separation begins. This phase concludes the extraction, leaving the concentrated amalgam ready for the final heat treatment. 20 to 30 minutes is the exact duration workers spend kneading the mixture with mercury to initiate a chemical bond. Why is such a manual process still utilized in these regions? Manual pressure forces the two elements to fuse into a gray, putty-like amalgam. But this is just the beginning. The mercury remains trapped within the metallic mass until intense heat is applied to the substance. One can notice how the flame causes the mercury to evaporate, vanishing into the atmosphere and leaving behind only a residue of raw gold. It only looks obvious that this is the most direct path to the metal, but in reality, the simplicity of this primitive method remains devastating to the environment. This lethal and archaic approach stands as the total opposite of how gold is extracted on the other side of the planet. In total contrast to the manual mining operations found in Africa, industrial sites in the United States have adopted modern machinery and advanced technology to extract gold on a massive scale. Such an approach not only increases overall efficiency, but also actively helps to reduce the environmental footprint of the operation. The process is only gaining momentum as it shifts to the gold mines of Nevada. Here, the journey toward the precious metal takes a fundamentally different path driven by technical innovation. 10 to 20 meters is the standard depth for the deep boreholes drilled into the earth during the first step of modern gold mining. An imponente drilling rig, mounted securely on a heavy-duty service truck and covered in a complex network of hydraulic lines, drives steel pipes into the solid rock with incredible precision and mechanical force. The equipment gradually penetrates the crust to prepare for the introduction of blasting agents. Why do engineers drill dozens of holes with such inch-perfect precision? At first glance, the placement might seem random, but it ensures the energy is distributed evenly. These voids are subsequently filled with explosives, which are carefully prepared to shatter thick layers of solid rock. Technicians place individual detonators into every single hole. One can notice how a single site may contain anywhere from 50 to 100 of these charges. Each one is meticulously connected and timed with millisecond precision to ensure a controlled sequence. Everything only gets more complicated as the final countdown begins. When the designated moment arrives, the explosives are triggered simultaneously. Powerful detonations shake the entire area with a low-frequency roar. It is visible how the rock face fractures instantly, sending dense clouds of dust and debris into the air as the solid ground is transformed into manageable ore. This concludes the primary fragmentation phase, opening the road to the next stage of material transport. Tens of thousands of tons of rock are shattered in a single moment as explosions release thick plumes of smoke into the atmosphere. The released energy is so extreme that it tears away entire sections of the mountain, disintegrating massive stone formations into thousands of smaller fragments. This catastrophic force is precisely calculated to simplify the subsequent collection and separation of the precious metal. Why is such a violent disruption of the landscape necessary? It only looks obvious that machines could dig the earth, but in reality, the rock is too dense for even the strongest equipment. Without these controlled detonations, the gold-bearing ore would remain locked within the impenetrable mountain walls. Heavy-duty excavators move into the blast zone as the dust slowly settles. With each mechanical cycle, the buckets scoop up several tons of ore and deposit them onto a sophisticated system of conveyor belts that stretch along the perimeter of the mining site. The equipment gradually moves the material toward temporary storage with mechanical consistency. But this is just the beginning. The conveyor belts operate as a fully automated network, ensuring a rapid and uninterrupted flow through the processing facility. One can notice how the belts glide over rollers at a constant speed, moving the jagged stones toward the next phase of refinement. It seems simple to process such a massive volume of stone, but in reality, the concentration of metal is incredibly low. Each ton of rock contains only 0.05% gold, meaning a single gram is hidden among thousands of kilograms of waste material. This tiny trace is not unreachable due to the deployment of advanced refining technologies that isolate the particles with absolute precision. The process is only gaining momentum. A massive ball mill receives the ore for the primary grinding stage. The giant machine is filled with tens of thousands of steel spheres, with individual weights ranging from a few kilograms to over 27 kilograms each. In total, several hundred tons of solid steel fill the rotating drum. One can notice the slow, rhythmic rotation of the mill as the internal load shifts. The steel spheres fall and collide with the ore with tremendous force as the mill turns on its axis. Little by little, the hard rocks are pulverized under the weight of the steel until they are transformed into a fine, uniform powder. This grinding cycle continues without interruption for 20 to 30 minutes, reducing the ore until it reaches the consistency of dust. Everything only gets more complicated as the extraction of the gold reaches its next critical chemical phase. 1120 degrees Celsius is the precise temperature required to bring the extraction process to its thermal conclusion. Why is the transition to a liquid state so critical at this final stage? The primary crushing of the raw material into a fine powder has already made the gold much easier and more efficient to handle during the initial phases. But the heat serves a different purpose, ensuring the metal reaches a state of total homogeneity before it is cast into its final form. Water is added to the crushed ore, transforming the dry mineral into a thick slurry that flows like heavy sludge. It is visible how this consistency allows the equipment to separate the gold from undesirable waste materials with greater fluidity. The extraction begins with a method that only looks obvious: physical separation in large open-air tanks. But this is just the beginning. Chemical agents, such as cyanide, are introduced into the mixture to dissolve any remaining gold particles still trapped within the ore. This solution is then pumped into an electrolytic cell, where a constant flow of direct current passes through the gold-bearing liquid. One can notice how the gold ions migrate steadily toward the negative electrode, gradually depositing themselves as a solid layer of pure metal that adheres firmly to the surface. Everything only gets more complicated as technicians monitor the environment. Every parameter is maintained under carefully controlled conditions to guarantee the resulting metal reaches a purity level of nearly 100%. The process is only gaining momentum. Once the electrolysis is complete and the pure gold has been isolated, the metal enters a high-temperature furnace. It seems simple to melt the metal, but in reality, this stage is designed to eliminate every last trace of remaining impurities. The camera glides along the surface of the melt as the gold turns into a glowing liquid at 1120 degrees. This liquid state allows the material to be poured into molds with absolute precision. High-temperature melting also makes the gold softer and more uniform, creating the ideal physical properties for shaping it into heavy bars. The casting process does more than just give the gold its standard industrial shape. It actively preserves the inherent purity of the metal as it transitions from a liquid stream into a solid ingot. The molten metal settles in an even layer within the mold, and the heat gradually dissipates as the bars begin to solidify. From here, the transformation moves to the next phase of processing without haste. 1,000 grams is the minimum mass a standard commercial ingot reaches as the molten metal begins its transition into a solid state. Why must the cooling process occur gradually in the open air rather than through rapid liquid quenching? Forced cooling could compromise the structural integrity of the ingot, causing internal stresses or surface irregularities that would ruin its commercial value. The liquid gold, having been poured into precision molds, slowly loses its thermal energy to the atmosphere. One can notice how the shimmering fluid surface dulls and stabilizes as the temperature drops. The equipment gradually settles as the metal hardens into a dense, clean, and perfectly rectangular geometry. At first glance, the bars appear finished once they solidify, but in reality, they must undergo rigorous metrological verification. Each unit is placed upon high-precision electronic scales to establish its exact mass with laboratory-grade accuracy. On average, these individual gold bars weigh between 1 and 2 kilograms. The chemical composition is remarkably consistent, containing 99.99% pure gold. This leaves less than 0.01% of residual metallic impurities within the final structure. The process is only gaining momentum. Technicians then subject the gold to a specialized cleaning phase using a mild acidic solution. It is visible how the liquid reacts with the surface to eliminate any trace of heavy metals or chemical compounds lingering from the smelting stage. Because gold is chemically inert to this specific reagent, the acid dissolves only the foreign contaminants without affecting the precious metal itself. Security protocols take over once the inspection is complete. Armored transport systems move the pure gold bars to the primary banking institutions of the United States, including the high-security facilities of the Federal Reserve. Here, the ingots are deposited into reinforced vaults under the constant surveillance of professional security personnel. Every movement is logged, and every bar is carefully preserved to maintain total confidentiality and maximum physical protection. Everything only gets more complicated when considering the physical properties of the finished product. The metal has traveled a long path from the initial blast in the mine to the final fusion in the furnace, yet its industrial utility remains vast. One can observe the extreme ductility of the material, which allows a single ounce of gold to be drawn into a wire finer than a strand of silk. But this is not the limit of its historical impact. During the gold rushes of the 19th century, entire populations abandoned productive farms and established cities in a desperate attempt to find wealth in the earth. It is a documented fact that many of these individuals found it impossible to abandon the search even when faced with total failure. The pure gold bar remains in the vault, ready for the next phase of its global circulation. 19,000 tons of rock must be excavated and processed to obtain a mere 260 grams of gold. This staggering ratio highlights the exhaustion of easily accessible deposits on the planet, a reality that forces miners to descend to unprecedented depths into the crust. Why must such immense volumes of earth be displaced for a handful of metal? While it seems like an inefficient expenditure of energy, the scarcity of the element dictates that even trace amounts justify the industrial effort. Only after surviving the trials of intense heat and complex chemical reactions do these 260 grams reach the workstations of specialized jewelry manufacturers. The journey continues toward the fabrication floor. From refined bars of pure gold, the material is transported under high security to facilities where the transformation into fine jewelry begins. One can notice how technicians place the bars into high-temperature furnaces to initiate the softening process. The equipment gradually raises the internal heat until the metal achieves a specific state of flexibility and malleability. But this is just the beginning. It only looks obvious that gold is soft, but in reality, achieving the exact structural consistency required for intricate work demands precise thermal control. Once the desired state of flexibility is reached, the gold is fed into powerful rolling mills. These machines exert intense, calculated pressure to flatten and stretch the metal into long, thin strips or incredibly delicate wires. The camera glides along the rollers as the thickness of the gold decreases with every pass, transforming the heavy bars into fine filaments. Everything only gets more complicated as the material moves to the next stage. Specialized chain-making machines receive the fine gold wires for the final structural shaping. The equipment rotates ceaselessly, winding the wire and forming it into small, precise links with millisecond timing. Each individual link is carefully assembled and joined to create a continuous, unbroken gold chain. One can notice how the automated manipulators align the gold with sub-millimeter accuracy. Every single gram of this glittering material preserves a detailed history of the power of technology and the exact price of human labor. These are two distinct sides of the same precious metal, representing both engineering mastery and physical endurance. The process is only gaining momentum as the focus shifts to another ubiquitous material. That cardboard box that arrived at your door today, which was opened and discarded without a second thought, does not represent the end of a narrative. In reality, it marks the commencement of an epic industrial journey involving global logistics and massive recycling infrastructure. Every year, the global industry processes more than 110 million tons of paper and cardboard to sustain the demands of modern commerce. At first glance, a box is mere waste, but it serves as the raw material for a colossal recovery cycle. The fibers are separated and cleaned as the material enters the pulping phase. This transition to the next level of the industrial chain ensures that the cycle of production and consumption continues without interruption. Thus, the material leaves the consumer's hands and moves back into the depths of the processing plant. 100 billion cardboard boxes are discarded every single year within the borders of the United States alone. Why is such a staggering volume of material not considered a terminal waste product? It would seem that these discarded layers are merely refuse, but the industry views this mountain of fiber as a literal gold mine. The structural secret lies in the fact that a single box can be resurrected 7 times before its fibers lose their integrity. Everything starts within the chaotic aftermath of daily global consumption. Behind the loading docks of supermarkets and within the vast distribution hubs of e-commerce giants, the sheer volume of discarded cardboard reaches colossal proportions. One can notice how powerful hydraulic presses engage with a mechanical hum, exerting immense pressure to compress loose piles of boxes into dense, uniform bales. Each of these structural cubes weighs exactly 1,000 kilograms. These units represent the primary stage of turning logistical chaos into industrial order. But this is just the beginning. Thousands of these 1,000-kilogram bales are hoisted onto heavy-duty trucks to begin a synchronized pilgrimage towards specialized recycling centers. At first glance, the arrival at the facility appears to be simple unloading, but in reality, the environment vibrates with the constant roar of massive machinery. Every single vehicle is weighed upon entry to track the incoming tonnage with absolute precision. The equipment gradually moves the material toward the first defensive line in the war against contamination. Transition to the next level. Inspectors and high-speed optical sensors operate in a continuous loop to identify and remove impurities that threaten the recycling process. The camera glides along the belt where the machines hunt for fragments of plastic tape, forgotten metal staples, and nylon threads. Even a small trace of grease or excessive moisture is flagged immediately, because a single error in this screening phase can lead to the destruction of an entire production batch. The vigilance is absolute. Therefore, the material undergoes a secondary sorting process based on the specific grade of the fiber. One can notice how the robust corrugated cardboard is separated from the thinner flat cardboard and boxes featuring heavy color printing. It gets more complex further on. Each unique category is diverted to a specific processing stream to ensure the final product meets the necessary structural standards. The material is ready to move to the next processing phase without haste. 1,000 kilograms is the exact weight of each individual bale, now standing in a clean and organized formation, ready for the next phase of its transformation. These dense blocks of recovered material must be completely deconstructed and returned to their primary fibrous essence before they can function as raw material once again. Why is such a violent mechanical process necessary for simple cardboard? At first glance, the material appears manageable, but in reality, only the immense hydraulic force of water applied at an industrial scale can break the chemical and physical bonds of the compressed sheets. The equipment gradually consumes the material within the hydropulper, which serves as the central hub of the entire facility. This giant vessel maintains a constant capacity of tens of thousands of liters of liquid, swirling in anticipation of its next intake. One by one, the 1-ton bales are dropped into this violent vortex with a heavy splash. The water inside is not a stagnant pool, but a controlled force of nature, driven by the mechanical heart of the machine. Massive rotor blades at the base of the tank rotate at hundreds of revolutions per minute. The camera glides along the perimeter where one can notice the intense turbulence creating a physical environment where the multi-layered structure of the cardboard is simply disintegrated. Hardened adhesive that once fused the sheets together is ripped away by the sheer friction. It gets more complex further on. Tinted inks and microscopic plastic coatings are stripped from the cellulose fibers like old skin as the mixture is intentionally diluted into a near-liquid state. In this suspension, only 1 to 2% of the volume consists of actual fiber, while the remaining 98 to 99% is water. Such extreme dilution provides each individual fiber with the necessary space to be surrounded by the liquid medium, allowing the water to attack the surface from every possible angle to clean and isolate it from its neighbors. What was previously a rigid, solid block of cardboard has now transitioned into a thick brown slurry, forming a uniform mass of cellulose. This represents the first glimpse of a new life for the material, yet the pulp remains coarse, structurally weak, and filled with residual impurities. Everything only gets more complicated as the process gains momentum. Before this substance can be converted into high-strength paper, the fibers must be reconditioned and reinforced at a microscopic level. The fiber soup is currently chaotic and lacks the internal cohesion required for industrial applications. How does a liquid suspension gain the structural integrity of a solid sheet? The answer lies in the refining machines, where the pulp is pumped through high-pressure lines to encounter rotating discs equipped with precision-engineered blades. This specific mechanical action does not result in the cutting of the fibers, but rather their delicate deflection. One can notice how the surface of each cellulose fiber is fibrillated, a process that opens up countless microscopic arms, or fibrils. These tiny extensions will later entwine with one another to form a chemical and physical bond of incredible strength during the drying stage. But this is just the beginning. It is visible how the equipment handles the reality that every recycling cycle naturally shortens and weakens the individual fibers. To rejuvenate the mechanical properties of the mixture, the facility injects a calculated portion of virgin pulp extracted directly from raw wood. This infusion acts as a reinforcement, mixing veteran fibers with new long-chain cellulose to stabilize the integrity of the final product. The material is ready to move to the next processing phase without haste. 100% precision in the blend of recycled material and fresh wood fibers creates the necessary equilibrium between environmental sustainability and structural durability. Why is the combination of these specific components so critical for the final product? The external layers of the future containers require a surface that is both exceptionally smooth and rigid, and therefore they receive a significantly higher concentration of virgin fibers. The internal section, known as the corrugated medium, consists almost entirely of recycled material, but the technical formulation is not yet finalized. It seems simple at first glance, but the recipe requires exact chemical intervention. Additives are introduced into the aqueous suspension with millisecond timing. One can notice how starch is integrated into the flow to provide essential structural stiffness. Special bonding agents are added to regulate water absorption, while specialized resins ensure the material remains resistant to environmental moisture. What began as a coarse pulp has now transitioned into a high-technology raw material. The process is only gaining momentum. 99% of the perfectly prepared suspension consists of water as it enters the paper machine, a massive engineering complex spanning several hundred meters in length. A thick brown torrent is discharged with mathematical uniformity across a wide wire mesh screen that moves at a vertiginous velocity. Everything only gets more complicated as the mechanical separation begins. Gravity and high-pressure vacuum systems pull the liquid downward through thousands of microscopic apertures in the mesh screen. One can notice the water departing from the fibers, leaving behind a thin, concentrated layer of cellulose on the surface. Now liberated from the liquid that kept them separate, the fibers begin to settle and interlock, forming a delicate and complex structural web. It looks outwardly simple, but the formation of the web determines the strength of the final sheet. Giant press rollers positioned beneath the moving screen gently squeeze additional water from the mass, compacting the new formation into a cohesive unit. The liquid visibly transforms into a solid state as the camera glides along the production line. Where a shapeless flow previously existed, a continuous sheet of paper now emerges, appearing pale and damp. Laser sensors monitor every millimeter of the moving surface with absolute accuracy. They measure thickness, uniformity, and moisture content to ensure that no defects interrupt this fragile stage of development. A new sheet of paper has been synthesized, but it remains heavily saturated. More than half of its total weight is currently comprised of water, leaving the material vulnerable and weak. To achieve its legendary structural strength, the sheet must now face a significant technical challenge involving extreme heat and mechanical force. The damp sheet is guided precisely into the press section. The equipment gradually increases the intensity of the physical processing. Pairs of massive steel rollers, each weighing more than a standard automobile, compress the sheet with a force equivalent to hundreds of tons. The water is literally crushed out of the fiber matrix, forcing the cellulose strands to unite in a more intimate and powerful molecular bond. One can notice how the thickness of the sheet stabilizes and the surface becomes smooth, but the raw power of mechanical pressure alone is insufficient for the final result. The material, now significantly stronger, moves deeper into the machinery as the transformation continues toward its next physical state. 100 meters is the minimum length of the thermal tunnel, where the damp material enters the drying section. Why is such an immense distance required for a process that seems like simple heating? A sudden increase in temperature would destroy the structural integrity of the fibers, making the final product far too brittle for industrial use. This massive installation ensures that the moisture evaporates with surgical precision, moving through a sequence of dozens of polished steel cylinders. These hollow, giant drums are heated internally by high-pressure steam. One can notice how the surface of the metal reaches temperatures exceeding 300 degrees Celsius. This level of thermal energy surpasses that of an industrial pit furnace, yet it is applied with absolute control. The paper web serpents through this incandescent labyrinth, maintaining constant contact with the hot metal. It is visible how the sheet glides over each successive cylinder to ensure the heat penetrates the fibers evenly. If the evaporation happens too rapidly, the paper loses its flexibility and cracks. Conversely, if the movement is too slow, the entire production line grinds to a halt. But this is just the beginning. A continuous stream of hot air circulates through the drying chamber to keep the moisture and temperature in a state. 5 to 7 times is the maximum number of cycles a single cellulose fiber can endure before its structural integrity fails. At first glance, the recycling loop for corrugated cardboard seems infinite, but in reality, each mechanical breakdown shortens the fibers until they are too weak to bond into a robust sheet. Why is this degradation so critical for industrial production? The answer lies in the physics of the material, as short fibers cannot create the interlocking web necessary for heavy-duty packaging. Therefore, these exhausted materials are redirected into the production of less demanding goods, such as egg cartons or paper napkins, where structural rigidity is not the primary requirement. Industrial rollers apply consistent pressure to ensure a perfect bond between the layers of what is now called corrugated cardboard. The process is only gaining momentum. This specific engineering creates a material that is simultaneously lightweight, inexpensive, and remarkably durable. One can notice how massive industrial blades slice, crease, and fold these sheets with millisecond precision, transforming them into the vast array of box shapes used globally. Everything only gets more complicated as the material moves from flat sheets to complex three-dimensional fortresses of paper. 10% of recycled material added to glass production reduces energy consumption by 3%. This fact highlights that recycling serves as a powerful force across multiple industries beyond just paper. It is visible how the cycle eventually closes when a discarded box from a warehouse corner is reborn as thousands of new units. Each container seen on a delivery truck or at a doorstep serves as a silent witness to this continuous transformation. The process does not end at this stage. 17 trees remain standing for every single ton of cardboard that is successfully recycled. Furthermore, this conservation effort saves 26,500 liters of water and prevents 1 ton of carbon dioxide from entering the atmosphere. It only looks obvious that a box is simple waste, but in reality, it is the starting point for a subsequent life cycle. The material reaches a standard ready for the further stage of its existence. Marmor represents a symbol of wealth and permanence found in palaces, museums, and high-end kitchens worldwide. One can notice the mirror-like shine on a perfectly smooth slab of this stone. But how is such a finish achieved from raw geological formations? The journey toward that polished surface does not begin with the delicate touch of an artist. It starts with a violent mechanical battle to extract a single block from the earth. The transformation moves to the next phase of processing as the stone is separated from the mountain. 70 feet is the exact height of the useless earth that engineers must remove before reaching the target material. Why must such a massive volume of rock and soil be destroyed? At first glance, it seems like unnecessary destruction. But in reality, this layer of overburden acts as a fortress protecting the valuable marble within. Without its complete removal, access to the high-quality stone remains impossible, rendering the entire operation stalled. One can notice how drilling teams begin the process by creating a precise grid of deep boreholes. This layer of 7 stories, equivalent to 21 meters of clay, silt, and debris, is systematically pulverized using carefully measured explosive charges. It gets more complex further on. The siren of warning cuts through the air, followed by a momentary heavy silence. Tens of tons of explosives detonate with a calculated delay, making the ground tremble as a massive cloud of white dust rises to obscure the sky. This is not chaotic demolition, but a surgical procedure performed with dynamite to strip away the mountain's outer skin. Thousands of tons of waste rock are torn from the slopes and tumble down the quarry walls with a heavy, rhythmic thud. Everything only gets more complicated once the dust slowly settles. The prize is a 40-ton colossus of stone that must eventually be transformed into a slab so perfect that a microscopic defect would make it worthless. The process is only gaining momentum. It seems simple to use explosives for the entire task, but in reality, the strategy must change the moment the marble vein is exposed. If the same brute force used to clear the overburden were applied to the marble, the internal structure of the stone would shatter. Therefore, the engineers transition to a method of absolute precision. The camera glides along a thick steel cable embedded with the hardest material on the planet, industrial diamonds. This wire is threaded through precisely drilled intersecting holes to form a continuous loop. It only looks obvious that a simple wire could cut stone, but this is a high-tech diamond saw. The machine activates with a sharp, constant hum that resonates through the quarry. One can notice the diamond wire beginning to saw through the solid rock at a steady pace. Simultaneously, high-pressure pumps deliver a continuous stream of water into the deepening cut. The water serves to cool the diamonds and flush out the fine stone slurry as the wire makes its way through the mountain. The transition to the next level of extraction is now underway. 2 distinct missions are performed simultaneously by the continuous stream of water directed at the diamond wire. Why is this constant lubrication vital during the extraction phase? At first glance, the setup looks like a simple cooling mechanism, but in reality, the fluid prevents the steel cable from melting under extreme friction while washing away the marble slurry, the fine white powder that forms as the stone is ground. The equipment gradually penetrates the rock at an agonisantiment slow pace, advancing centimetro by centimetro through the solid mass. One can notice the mechanical tension rising as the groove becomes deeper. Workers insert hydraulic jacks into the narrow crevices with measured movements. Using a silent force equivalent to hundreds of tons, the pistons begin to push against the ancient stone. A deep groan echoes through the quarry, which is the physical sound of the mountain finally surrendering to the pressure. It gets more complex further on. 40 tons is the weight of the massive block that finally separates from the mountain face, standing as tall as a 3-story building. The block is free, but it immediately transforms into a 40-ton problem for the logistics team. This mass is equivalent to the weight of 30 average cars or 6 full-grown elephants concentrated into a single geometric shape. It is impossible to simply drag such a colossus across the uneven ground because the risk of fracturing the expensive material is too high. Therefore, the slab must first be moved with extreme caution to a waiting yard, which serves as a flat and secure staging zone located within the quarry perimeter. True giants of the industrial world enter the scene at this stage. Heavy crawler cranes, machines specifically engineered to lift impossible loads, begin to position themselves around the white stone. Massive steel chains, featuring links the size of a human head, are secured around the block with heavy clanking sounds. One can notice the crane motor laboring under the initial strain, producing a deep, guttural roar as the hydraulics engage. The tension in the steel links becomes absolute as they stretch to their limit. Precision of a master is required from the crane operator during this delicate maneuver. The stone colossus is hoisted from the ground with millimetric accuracy to avoid any sudden shifts in the center of gravity. The block is then carefully lowered onto a specialized transport vehicle that barely resembles a standard truck. It is a low-profile platform trailer equipped with multiple axles and dozens of heavy-duty tires. Why are so many axles and wheels required for a single load? To the eye, the trailer design seems redundant, but 40 tons concentrated on just a few contact points would instantly pulverize any road surface. By distributing the weight across dozens of wheels, the pressure becomes controllable and the infrastructure remains intact. Safety checks are performed 2 or 3 times by the crew before the journey commences. The truck moves at a snail's pace, beginning the slowest journey imaginable as it climbs the steep, winding mountain roads. Each curve represents a complex logistical challenge, where the trailer must be positioned perfectly to avoid the edge. Every descent tests the braking systems to their absolute limit as they fight against the momentum of the 40-ton mass. This slow-moving convoy is transporting the raw material from its original geological home toward the factory. The molten stream of production is only gaining momentum as the stone leaves the mountain. From here, the transformation moves to the next phase of processing. 40 tons is the exact weight of the monolithic block as it arrives at the industrial facility. Why does the air inside the plant lack the sharp scent of explosives and quarry dust? The atmosphere here shifts toward the heavy smell of wet stone and cold metal. This creates a distinct sensory contrast compared to the extraction site. Hydraulic clamps of immense proportions descend upon the block to fix it onto the cutting platform with massive force. The equipment gradually tightens until the stone is immovable. One can notice how the block remains perfectly still, as a deviation of even a single millimeter during the cutting process would result in crooked slabs. At first glance, the setup seems simple, but in reality, any movement ruins the entire batch. The machine waiting to process the stone is known as the gang saw or frame saw. It consists of an enormous structural housing designed to support the weight of the block while holding a giant frame equipped with dozens of parallel blades. Arranged like the teeth of a massive comb, these blades begin their work with a rhythmic and deafening roar. The frame moves back and forth, establishing a brutal and hypnotic pace. But this is just the beginning. Abrasive-coated blades begin to descend millimeter by millimeter into the 2-meter-thick stone. Simultaneously, a continuous stream of water and abrasive sand pours over the cutting area. This abrasive slurry acts as a lubricant and cutting agent, helping the metal blades bite deep into the rock. It is visible how the gray mud splashes against the machine walls as the incredible noise fills the hall. The process is only gaining momentum. For a single block of marble, the machine may require between 12 and 20 hours of continuous operation. 12 to 20 hours represents an entire working day, or even more, dedicated to sawing a single piece of stone. Patience serves as the most critical tool in this factory. It gets more complex further on. Finally, after nearly a full day of mechanical labor, the blades pass completely through the bottom of the block. What was once a solid cube is now transformed into a giant deck of cards. A set of stone slabs remains, with each individual piece weighing hundreds of kilograms. One can notice how the slabs appear lifeless at this stage. They are dull to the eye and rough to the touch, possessing a pale color masked by the gray mud left behind by the cutting process. Everything only gets more complicated as the famous beauty of the marble remains hidden beneath the surface. Now the physical transformation begins. Automated robotic arms enter the workspace to take over the heavy labor. No human hands are used here because the slabs are both too heavy and too delicate for manual movement. Giant vacuum suction cups descend with the hiss of pneumatics, gripping the stone before lifting it into the air. The robot maneuvers the slab onto the polishing line, which functions as a long tunnel of transformation. The slab slides slowly under the first station, where a set of rotating heads waits to begin the refinement. Transition to the next level. These rotating heads represent the first step in revealing the stone's inner texture. 8 automated grinding heads are equipped with specialized abrasive discs to begin the transformation of the stone surface. Why is the sequence of these grinding stations so strictly regulated? It would seem that a single pass could achieve the desired smoothness. But without a gradual transition between grit sizes, the deep structural gouges from the initial processing would remain permanently embedded in the material. The process commences with exceptionally coarse grains, functioning like an industrial-strength sandpaper designed for heavy material removal. One can notice how the slab advances steadily as a harsh, violent rasping sound fills the facility. echoing the friction of stone being forcefully abraded. The first layer of resistance is broken here, but this is just the beginning. The second station features discs with significantly finer grains to refine the surface. The acoustic profile of the workshop shifts immediately as the grinding sound becomes noticeably higher in pitch. At the third station, even finer abrasives are applied to the slab. It is visible how the stone passes through a minimum of 7 or 8 distinct sanding stages in a continuous line. Each subsequent phase is designed to remove the microscopic scratches left by the previous disc, making the surface progressively smoother to the physical touch. Throughout this entire sequence, the equipment operates under the constant pressure of falling liquid. Toneladas of water pour over the machinery to cool the rapidly spinning discs and wash away the thick marble slurry generated by the abrasion. This prevents the stone from overheating and ensures the abrasive grains remain unclogged. Everything only gets more complicated as the slab reaches the final station. This specific unit does not utilize abrasive grains at all. Instead, it employs a specialized chemical polishing compound applied under intense pressure. The heads rotate at high speeds, and the dull gray stone suddenly undergoes a physical transition into a reflective mirror. Where the surface was once matte and lifeless, a deep, brilliant finish now appears that captures and redirects the ambient light. Colors explode across the surface as the hidden veins, locked away for millions of years, are finally revealed to the eye. At first glance, the polished slab looks absolutely flawless, but in the luxury market, appearance alone carries no industrial value. The most dangerous defects are those that remain hidden from human perception. One can notice the slab gliding silently into a specialized dark chamber for the next level of verification. It is here that a laser inspection system begins its work. Intense beams of red light sweep across the entire surface of the stone at high frequencies. The laser performs a task that the human eye is physically incapable of completing. It measures the absolute flatness of the material and searches for internal microcracks that could compromise structural integrity. The equipment identifies every minute anomaly, from a tiny trapped air bubble to an invisible stress line caused by the original quarry explosion. It only looks obvious that the stone is solid, but in reality, the computer must analyze every millimeter of the laser image for discrepancies. If the system detects the slightest imperfection, the slab is immediately marked with a red indicator. Rejection occurs instantly. Even after the immense labor of polishing and grinding, the compromised stone is discarded from the premium line. The process is only gaining momentum for the slabs that pass this rigorous digital screening. Only the perfect specimens are allowed to proceed further through the manufacturing chain.